So hi everyone, in this video we are going to solve this particular problem on GFG, that is string rotation of each other. So what is the problem? In the problem we'll be given two strings S1 and S2, and what do we need to do? Uh, the task is to check if S2 is rotated version of S1. Okay, a string is a rotation of another string if it can be formed by moving character from start to end or vice versa without rearranging them. Okay, so S1 is somehow rotated to some particular. Uh, okay, so S1 is rotated, and that's how S2 is formed. We need to check if that is true or not. So, for example, in the first example, ABCD can be rotated to its right for two index, and it could form S2, so that we can say that okay, it will be true. Same for S1. For the second example, okay, let me try it here. Okay, so some string might be there ABCD. So suppose D is erased from there and moved to here. So now the string will look like this, DABC. Now suppose C is deleted from here and moved to the first index. So C will come over here and CDAB. So this will be the new string after rotating it twice. So we'll be given this string ABCD and the string that could be there after rotation. ABCD, and will be given the rotated form CDAB. We need to check if that is true or not. Like by true, I mean if rotating the string S1 could form S2 or not. So, we need to check that. So the naive approach would be to check check like this. So by performing one operation after another and checking whether it is forming the string or not. For example, let's say this one is the example ABCD and SCBT. Suppose S1 is ABCD and S2 is ACBT. So what we can do, we can perform one operation after another and check. So suppose D will be moved to here. So D will come to the first index, then there will be A, then there will be B, then there will be C. So we'll be checking this string with this one, if both of them are same or not. So no, they are not same. Then we'll again perform this operation. So C will come here. So C, D, A, B. So after this operation, it will form this string. So this one will check with this. Uh, these two are not same. So we're going to again move forward. So B will come here and B, C, D, A. So we can check and we'll be like, okay, these two are not same. So again, A will come forward. So it will form A, B, C, D. And we'll be again checking that, okay, this string is same as this one or not. Because this is not same. And again, if we see that we have come to the same string that we have started with. So we can say that, okay, there is no need to check anymore. So there is no way we can form S2 by rotating S1. So if we are not able to form S2 rotating this one, we will return false. As simple as that. And otherwise, if at any step we are able to see that okay, both of the string are same, then we can say that okay. Otherwise, we will return true at any step. That's what happened for the first example. That is it. That rotating the string twice will lead us to CTAB, which was history. So that's when we are returning true. But what is going to be the time complexity for this one? So for each rotation, uh, so taking the string from here and putting it back over there. So this one is going to lead us to big of n time complexity. Why? Because after putting this character over here, we are going to shift all the character to its right by one. So suppose A was at 0 index, B was at 1 index, C was at 2 index. So now A will come to 1 index, B will come to 2 index, and C will come to 3 index because B took the position of A. Same for the other operation. A was at 1 index. Now A will get 2 index. Why? Because D took the 1 index. And why D took the 1 index? It was at 0 index to the front. So that's why all the element will be moving to its right by 1 index. So this whole process will take linear time complexity, that is big of n time. So that's why we are not going to solve this. Able to solve this by this approach. Why? Because if we try to do it for all the characters, so there can be at max there can be n characters. So for each of the character, if we perform big of n operation, then the total time complexity will come up to big of n square. So that's not what we are looking for. Why? Because if you see the size of n could be as big as 10 to the 5. So if it turns out to big of n square solution, then 10 to the 5 to the power 2 will lead us to 10 to the power 10, which is greater than 10 to the 8. So that's not what we are looking for. So we need to see for more optimal solution. So let's see how can we get to the optimal solution. Okay, let's see. Mm, what can we do? Let's take one example where it is getting true. So A, B, C, D and C, D, A. Okay, so let's take this example. So suppose this one is A, B, C, D and it is C, D. So this one is the rotated version of this one. So how can I say that? So, okay, there is this concept of KMP algorithm. Maybe that's what they are using. But KMP is a very complex algorithm. Do we need to do that KMP or Z algorithm? Uh, so basically, what they are going to do, they are going to check for each index what is the most number of characters that are going to match from the starting of this. Okay. Okay, then after that they are going to solve it. So this is a pretty trivial solution. If that is the case, then I'm not going to discuss it. Uh, let's see in the hint. Are they going to use KMP? Try and continue effects into that later. Contain all possibilities. Okay, they are going to use KMP. So KMP is a pretty complex solution. Uh, this algorithm is the prerequisite for this problem. So if you have not gone through KMP algorithm, then first you should go through that. I'll not be explaining this in this video, but yeah, hope you'll find this explanation helpful and hope you are able to understand why we are going to need KMP for the solution. I'll, be, I'll stop recording this video as of now. And yeah, maybe I'll record the explanation of KMP some other time, but not in this one. So bye.